Well, our next topic is the preliminary theory for equations of higher order. And an equation of higher order means it has more than a first derivative in it. This example here has an nth derivative in it, see? Some function times dn of y over dx to the n, that means the nth derivative of y, plus another function times the n minus first derivative of y, plus etc., all the way down to another function times y equals g of x. If it's g of x, then it's not homogeneous. But with initial conditions, now we're going to have as many initial conditions as we do derivatives. So we need an initial condition, a value for y, a value for y prime at x sub 0, and a value for the n minus first derivative at x 0. So we'll have to have n initial conditions to solve an nth order equation. If you think about it, if you integrate something n times, you're going to get n constants of integration. So therefore you will need n initial conditions to solve for those constants. So are we ready?
I'm ready, so let's go.
Okay, so let's look into this. If we have a set of functions, a sub n of x, a sub n minus 1 of x, and finally a sub 0 of x, that's not supposed to be a subscript there. Bear with me for a second. There, that's what I want it to be. And g of x is continuous on some open interval I, and let all these, well, actually let the nth function not be 0 for all x in that interval. Then if x equals x of 0 is any point in the interval I, then the solution of this differential equation, this one, exists and is unique. So here's an example. Given that y equals c1 plus c2 cosine x plus c3 sine of x is a 3-parameter solution of, notice this is y triple prime plus y prime equals 0. So there's 3 derivatives in this equation. Therefore we will need 3 constants, c1, c2, c3. Find a member of this family satisfying these initial conditions: y of pi equals 0, y prime of pi equals 2, and y double prime of pi equals -1. Notice we have, this is a degree n equals 3 equation, so we need initial conditions for the function, its first and then its second derivative. So we need conditions for up to the n minus first derivative, as in this particular characterization of what we're doing here. Okay, let's go back to this now. Since sine of pi equals 0, right? So this is 0, so this part is 0, and cosine of pi is -1, so what we have is, from this initial condition, y of pi equals 0, we have 0 equals c1 minus c2. I hope you can see that. We also have y prime, so we've got c1 minus c2 equals 0. Y prime would be negative c2 cosine x plus negative c2 sine x plus c3 cosine x. So that's our y prime, and when we put pi into that, sine of pi is 0, so this part of the equation is 0, and this part, remember, it would be -1. So -1 times c3 equals 2. So therefore c3 has to be -2, right? And also we know the second derivative of this, recall that the first derivative is here, so the second derivative would be the derivative of this. Well, there'd be negative c2 cosine of x minus c3 sine of x. So there's our second derivative, and we know that second derivative evaluated at pi equals -1. So cosine of pi is -1, so we got -1 here equals -1 times c2, so positive c2, and of course sine of pi is 0, so -1 equals c2, so c2 equals -1, and the unique solution is y equals -1 minus cosine of x minus 2 times the sine of x.
Nice work.
Thank you.